All right, welcome everybody. So we've been working with moving between different bases for R2 so far. Now what I want to do is define how we can construct a change of basis matrix between two different bases for any arbitrary vector space V. So now we can think about vectors V that might be functions in matrices and some of these other more abstract vector spaces that we've been working with. So let's say I've got one basis B, which consists of vectors b1, b2 up to bn. And again, now I'm using the term vector more abstractly. And we have a second basis for this same vector space V that will denote C, and it consists of vectors C1, C2 up to Cn. So we know that these two bases have to contain the same number of elements. So then we can define a unique change of basis matrix, which is going to be an n by n matrix because we're mapping from a space that is spanned by n vectors into a space that is spanned by n vectors. So we're going to denote this change of basis vector with a p consistent to how we've done this before, and then we index this p with a subscript here which has B mapping into C. So this means changing from B into C. And we've seen that one way to do this is to go ahead and start off in your B matrix world, map up to V with respect to some standard basis, and then map back down to C by taking the inverse of the change of basis matrix for C. So we can do this in two stages by first multiplying whatever our vector is with respect to B coordinates by the change of coordinate matrix P sub B, and then we map by the inverse of the change of coordinate matrix P sub C. So we can write this as first multiplying by P sub B, and then multiplying on the left by P inverse sub C. So this is going to map vectors in V written with respect to B coordinates all the way over into vectors still in vector space V, but now they're going to be expressed relative to basis C in C coordinates. And so one way to do this again is by multiplying the two matrices, P sub B and then P C inverse. And what we'll see in the next example is that this change of basis matrix from B to C, we can also write by taking each of the basis elements in basis B and expressing each of these in terms of their C coordinates. So that's what this matrix is denoting here. We take basis B1, basis vector B1, we rewrite it with respect to C coordinates. We take basis vector B2 and we rewrite it with respect to C coordinates. This matrix is going to be consistent, is going to be equal to the matrix that we get when we first go P sub B and then go P inverse sub C. Okay, so let's take a look at this example that we have been working with where our vector space V is R2 and we've got two different bases. Basis B has vectors 2, 1, and -6, 1. And basis C has vectors 5, 3, and 2, -2. And we want to come up with the change of basis matrix from B to C. And so before we've been kind of doing this in two steps, going from B to standard basis and then standard basis into C. And if we combine those two steps by taking the product of those two corresponding change of coordinate matrices, then we can find one matrix which is going to convert from these two bases. So we can kind of eliminate the intermediate stage of mapping into the standard basis. So for this example, we have the following two matrices that we can multiply. So the change of coordinate matrix from B coordinates to the standard basis would just be the matrix whose first column is 2, 1, and second column is -6, 1. So multiplying any vector relative to B coordinates by this matrix puts us in the standard basis. And then we apply P sub C inverse. So now I take the inverse of PC. So PC would be the matrix 5, 3, 2, minus 2. We found that the inverse of that matrix is minus 1 over 16 times the 2 by 2 matrix whose first column is minus 2, minus 3, and second column is minus 2, 5. So if I take the product of these two matrices, then I wind up with the matrix which I can write as 1 over 16 times the matrix whose first column is 3, 1, and whose second column is minus 10, 3. So this again is obtained by first going PB, then going PC inverse. So I want to just map out another way that you could organize your work to find this change of basis matrix. So we can start with this sort of augmented matrix where we start with two column vectors corresponding to basis C. So this first matrix over here, 5, 3, 2, minus 2, this is the change of basis from C into the standard basis. And then we have on the other side of this vertical line the two column vectors from basis B that make up the change of basis matrix to go from B into standard coordinates. So that would look like 2, 1, minus 6, 1. And then what we want to do in the end is take this matrix of columns of B and multiply it by P sub C inverse. And so one way that we can multiply by the inverse would be, let's apply row operations for the first piece of this matrix that consists of the column vectors from basis C. Let's do row operations on this matrix so we get the identity matrix over here. And that's going to be consistent with applying elementary row operations, which are going to add up when I apply this whole sequence of elementary row operations. It's going to be equivalent to inverting the matrix C. So for example, we could start with this matrix, which has C1, C2, B1, B2, and then I start applying row operations so that the matrix of columns from basis C, I start to write it as the identity matrix. So for example, I could scale the first row by 1/5. That gives me 1 2/5 in the top row. And I also apply that to the top row on the other side of this vertical bar. Then we could multiply this scaled row by -3 and add it to row 2 to replace it. And you can check my calculation. That would give me this matrix. And then we continue this process. And at some point, we get down to this matrix where we have the inverse on the left. And the stuff on the right of this vertical bar is exactly going to be the change of basis matrix from B coordinates to C coordinates. So this is consistent with the result that we got over here. So you can do this either way by finding each of these matrices separately and then taking their product, or by setting up this augmented matrix and applying row operations so that you get the identity matrix on the left of the vertical bar, and what's on the right of the vertical bar is going to be your change of basis matrix. And in the previous theorem, we were told that this change of basis matrix from B coordinates to C coordinates, we can also find this by taking B1 and writing it in C coordinates. That's going to be the first column of the change of basis matrix. And then taking B2 and writing it in terms of its C coordinates. And that's going to be the second column of the change of basis matrix. And so, for example, the first column vector 2, 1 has C coordinates 3 over 16 minus 1 over 16. That's this first row of the change of basis matrix. You can check that if I take 3/16 times C1, 5/3, minus 1/16 times C2, which is the vector 2 minus 2, this does give me 2, 1. So this first column of 3/16 minus 1/16 is the vector 2, 1, B1, written with respect to C coordinates. And similarly, 6, 1 has C coordinates minus 10 sixteenths, minus 23 sixteenths. So this is consistent with that previous theorem. So here you can see there are several different ways that you can find the change of basis matrix from B into C, and which method you use might depend on what sort of information you are given. In this case, we were just given two bases, P, B, and C, and so either taking the product of PB and PC inverse, or by going through this row operation process, is going to give us this change of basis matrix.